I'm going to be giving a presentation on the Ceph solution design tool that we developed at OSNexus. This is a lot of what I do day in, day out, is designing Ceph clusters for customers. And we're going to touch on some of the points that Anthony touched on the last call, but with some more graphics so we can kind of dive into that in a bit more detail there. And so this is what those design utilities look like. You can essentially indicate how much capacity you need for the design, and then start choosing some of the hardware and hard drive sizes and things like that. And you can design the whole cluster, and it'll give you the whole bill of materials down here at the bottom. But kind of getting started with this, you got to start whenever you're designing a new cluster for any use cases, gather a bunch of information. And so a lot of it's really consultative at the beginning of a discussion with any customer, because we really want to get the very best design that we can and reduce the amount of cost for deploying that design by reducing the amount of hardware, choosing the right EC level so they get the maximum durability and cost savings out of their Ceph cluster. So one of the big things right off the top is we got to know how much usable capacity they need for the deployment. Is it a petabyte, 500 terabytes? All these kinds of things help inform what hardware we're going to choose. We're going to also identify the primary use case. And like Anthony was getting at on the previous talk, if we choose a use case, if their use case is like virtual machines and databases, it's going to be more IOPS focused. We're going to end up choosing a layout like replicas versus erasure coding. Durability and performance requirements, if there's a need for hitting a particular benchmark, like, hey, I have to have 50 gigabytes per second, that's also great to know, because Ceph scales with the more devices that you add to the cluster. So if you are not yet at the performance that's needed, you just keep throwing more hardware at it. And one of the ways that we can throw more hardware at it is reduce the size of the hard drive or the size of the SSDs or both. Because if we have 15 terabyte SSDs in there and we drop it down to 7.5 terabyte SSDs, that'll double the performance for us for the same capacity. Then we go into figuring out, is it a single site or multi-site cluster? That'll also inform things. And then are there specific hardware preferences? Inside the design utilities, we've got all these different vendors baked into it, so you can pick between, Supermicro, Dell, HP, a bunch of different hardware vendors have equipment in the design utility, and we keep adding to it on a regular basis. So if you're out there designing a cluster and there's a particular server that you want to see in the design utility, just send us an email at info@osnexus.com. We're adding more hardware to the design utility all the time. And then we're going to go into a little bit more about the logic behind the tool. What's all the math that we're doing behind the scenes to come up with these numbers and recommendations? And then at the end, I'm going to give you a couple of demo designs. We'll go into the design utility and move some of the sliders around, and then just do some quick Q&A. So with that, one of the key things that we got to do at the beginning, pick the target capacity or identify the target capacity. When things are fairly small, like Ceph, we really don't like to use Ceph when it's a really small need. Like if it's 20 or 100 terabytes, it's not really taking advantage of the Ceph architecture much. But there are some nice servers that you can use for really low density clusters. And like this example here, this box from Supermicro has like 6 NVMe slots and 10 hard drive slots, and you can use 1U servers for these really small type applications. When they start getting bigger, we start getting into some bigger chassis. This is a bigger Supermicro chassis. This is an XD2 chassis from Dell. It looks like it only has 12 drives, but actually has room for 20 because there's a whole bunch of bays on the interior. And these generally have like 4 NVMe slots. And when we're talking about medium density all flash, there's 60 terabyte NVMe drives available. So 24 times 60, you're over a petabyte in a shelf. So you can get to some great capacities just with a single using these 2U24 bays. And then when it starts getting into really high density Ceph clusters, our building blocks get really big. And this is a 36 bay NVMe. This is what's called the Seagate Core Vault, and it's a smart JBOD. I'll talk a little bit more about this at the end of the talk. It basically does erasure coding in the chassis so that it eliminates some of those Ceph cluster problems that Anthony and Dan had pointed out, where if you've got a really big cluster with 2,000, 3,000 OSDs in there, you're basically going to be always healing that cluster. It's always going to have degraded hard drives in that cluster. Wouldn't it be nice if you localized it? And that's what this is all about. It makes it so your Ceph cluster is always healthy because the drive failures are handled locally within the chassis. So after we've identified the target capacity and kind of have a rough idea of the servers, we want to know a bit more about the primary use case. And really, these are all your use cases here where we're going to go use basically a replica-based layout. If it's a database of pretty much any kind, it's going to be doing all kinds of small writes, 4K, 8K, 16K writes, and you want to use replica as the format for that. That includes vector databases, which are heavily used in AI today, containers, virtual machines. Those are all high IOPS workloads, and so when we're figuring out how much storage we need, usually that's going to be all flash replica 3. That chunk we're going to set aside as, okay, that's for the high IOPS part of the workload, if not all of the workload. And then basically, throughput is everything else in the world. If it's not one of those things that's doing a lot of small block I/O, we get to use erasure coding. And so we get to design the cluster to be way more efficient. And this is for backups, archives, CCTV, content delivery networks, most media and entertainment workloads, all the big higher education, big workloads from astronomical data to genomics, and even big things like seismology data that gets collected by oil and gas. So it's really it's two flavors. The whole division of a Ceph cluster or a storage cluster, it's really two major categories, IOPS or throughput. And we identify that and early on. And if there's a split where you need to do both, then we kind of partition that cluster out and make sure that there's a percentage that's designed for that IOPS piece and a separate percentage that's designed for the throughput. So you can have a mix of replicas and erasure coding. I wanted to kind of dive into a little bit on the durability part, which Anthony touched on as well. But when you, the way that Ceph works is you've got a bunch of servers. They're all working together. They've got a bunch of devices, which are called OSDs. And then you create these pools of storage to store your data in them. The pools are thin provisioned, meaning that they use space on the OSDs as it's available. And they have this logical mapping between the pool itself and the OSDs that are called placement groups, which are those PGs on the end. And they are, in this example, we're showing a 4+2 erasure coding. As Anthony had talked about, we've got X many K blocks. These are the data chunks, and then these are our coding chunks to protect it. So we've got 4K plus 2M. And you want to design the cluster so that if you lose a box, you're still running, right? So you get the Donkey Kong in here. This server's off for whatever reason. Could be just doing a firmware update that requires a reboot. This is going to be offline for a certain amount of time. And in order for the cluster to keep running, I kind of colored the OSDs in a darker color blue here to indicate that these are like the coding block OSDs. You need to have at least one of these dark blue OSDs online at all times. And so if you had another failure while this box was offline, this is an example of where Ceph is going to stop the pool to protect itself. So this is where we do a lot of planning up front. If we need more durability than this, then we might do a 4K plus 3M to have another coding block so that we'd have these all be dark blue, and this would be, instead of K, it would be M. So, yeah, question?
Where you lose that drive in server 5?
Yeah.
Does that become read-only, or does it go offline?
It basically goes offline. You can, this is where you set the, there's a min size of chunks that have to be available. And with erasure coding, it's K plus 1. And this would get it below that because you can see for this placement group, which the brown line connects, you can see it lost this one and that. So it's down to 4 pieces. And because that one placement group got down to 4, the rule is that it will stop. You can go in there and adjust it and say temporarily I want the cluster to keep running even though I'm not meeting that durability. I just have K blocks. We just generally don't recommend running it that way for any significant amount of time. It's more for like recovery type activities. So you want to design the cluster with enough durability such that you can lose a server and also lose a device. And one interesting thing here too is you can use some tricks to keep the durability at this, or the usable capacity at the same level. This is also on Anthony's slide. Instead of 4K plus 2M, you can use 6K plus 3M, and you've just upped the durability so that now you can lose a host and lose a drive and not have any downtime at all. So you don't have to always sacrifice usable capacity to get more durability. You can kind of extend the stripe length to achieve the same goal. So this next one is multi-site. I wanted to touch on this as well because this is becoming more and more popular, doing multi-site Ceph, and it's the same kind of thinking. It comes in and you have a site outage, so you've lost both servers 5 and 6. So we've lost 2 coding blocks, but we still have 1 left over, and so everything keeps running with the remaining sites. And so when you design these Ceph clusters, you want to make sure, again, that you pick a K plus M combination that's going to be able to survive the outages that you're planning for. So yeah, that's on multi-site, and this is one of the really neat things about the Ceph architecture is you get to pick any combination of K plus M, and that's not universal. There's a lot of products, storage products that are out there that support erasure coding, but don't have that level of flexibility where you can just pick any arbitrary K for the data chunks and M for the protection coding blocks. And this, again, this similar kind of thing. This 3 plus 3M, this would stop the cluster in this case because there's some placement groups here that no longer have any of these coding block, the dark blue ones. But again, we can solve this by doubling these up and going with a 6K plus 6M and get the same durability, same usable capacity of 50%. All right, so a little bit of the logic behind the tool before we dive into it. We've been working on this tool for a long time. Like 2018 is when the first version of the QuantaStore design utility for Ceph came out. And it was really, it came out of the necessity because we were producing tons and tons of new diagrams in Visio. And it was just painful because what would happen is you'd make a cluster design and then the customer would say, well, this looks great with 12 terabyte drives, but can I see this with 10 terabyte drives? And you're back to square one, right? You got to do all your math all over again, recalculate everything. And so you're just spending your time in sort of Visio hell. And we wanted to eliminate all of that, but we also wanted to put smarts into these, into the utility because you've got folks that like Anthony and Dan and experts that have been out there building clusters forever. And we wanted to put some of that institutional knowledge right into the design utility and also have it produce benchmarks because benchmarks are so expensive to produce and very difficult to produce when you're saying, hey, what's the performance of a 50 petabyte cluster, right? You want to be able to get those numbers over to the customer with some solid numbers that they can work with so that when they go put that multi-million-dollar investment into the cluster, that they're gonna know what they're gonna go get. And so what we did was we took a lot of the benchmarking work that we had done with hardware partners, and then we combined that with various data that was in the open source, out there in blog articles, even some from Clyso helped inform some of the equations that we built, and those equations produce best fit lines through that real world data so that the numbers that you get in here, which you'll see on the right-hand side, these are throughput numbers and these are IOPS numbers. Those are all based off of synthetic equations that are based off of real world data. So that's where the performance numbers come from. The RAM requirements, Ceph likes to have about 4 gigs of RAM per hard drive, about 6 gigs of RAM per SSD. And that varies a little bit. Some folks will say 8 gigs per SSD. If it's a really fast NVMe, you might want a bigger cache there. That's all built right into the utility. So as you start moving those sliders around and it starts adding more devices, it's automatically adding more RAM. It's also adding more CPU cores. So as you adjust things around, there's a drop-down list of all the processors available on that platform. It's going to dynamically adjust that and add more cores. It's going to pick a bigger and bigger processor as you add more and more NVMe devices to the cluster. So it really guards against a lot of the common mistakes in cluster design. So that's where the RAM and CPU requirements come from. And then last but not least, the network requirements. Anthony had talked about this in his talk, is there's space amplification or write amplification. When you go and write a piece of data and it's 1 megs and you're using replica 3, that's going to turn into 3 megs of data that's actually stored in the cluster. And so you've got clients pushing the data into the cluster, and then the cluster has to then redistribute 3 times as much on the back end. So you can kind of think of that as 1 unit in, 3 units out. You have these 4 chunks of 4 pieces. And then if you were to go and figure out what is the maximum throughput of all my devices, how much network bandwidth would I need with that level of amplification to just make this cluster run at its full speed? So that math is all done within the design utility, and that's where this min recommended networking comes from. It goes and does all that amplification math based off of your choice of erasure coding or replicas. So if you go from erasure coding layout to a replica layout, you might see that it says, hey, you need more network, bigger network cards, whether it's going from dual 25 gig up to dual 100 gig. And of course, you can adjust things on your own. You can go here and adjust the Ethernet ports or adjust things like the processors, and that's what all these sliders are for, because once you kind of dialed things in a bit, you might want to dial them in a little bit further based off of more information you get from the end user. So that's the bit behind the tool. How do we come up with it? Some of the work in producing these. And last but not least, I'm going to just kind of go right to the design utility. It's on our website. You can get to it through these QR codes, but if you just go to OSNexus.com Ceph Designer, or if you just go into Google and put in Ceph Designer, it's like the top link for designing Ceph clusters. So I'm going to go through, to wrap up, 3 example designs. We'll start with like a 1 petabyte Supermicro all flash, and then we'll go from there to looking at like a 500 terabyte hybrid. So the all flash is a great example for like Kubernetes and OpenStack, all these types of virtual machine workloads where you're going to want an all flash configuration to focus on that IOPS. The second one is going to be more for like Veeam backups, an object store for Veeam backups, where you might need 500 terabytes of hybrid. So it's going to be hard drives that are accelerated with some amount of NVMe. And then the last one, we're going to go look at it, sort of a mega, a big config, 50 petabytes using the Seagate Core Vaults, which are these units here. So let's jump into the first one. And hopefully I can get to that link here from the slide. Here we go. And I'm going to zoom out a little bit because we changed the resolution here to 1080p, no worries. There we go. And I'll just scroll down a little bit. This will be all right. Yeah, control minus. There we go. There we go. So, yeah, I remember talking with a customer that there's a lot of misinformation out there about Ceph because it's been around for so long, and the early versions of Ceph had all kinds of challenges. Before BlueStore came out, there was a file store where it was actually writing to an XFS file system, and so some of the challenges we run into is just sort of bringing people up to speed with all the cool things that Ceph can do, and how many of these performance problems that are just long history. But one of the things that you can do with the cluster is you can just very easily adjust the performance just by adjusting the device count. So here we're showing a cluster that's 1 petabyte with 9 nodes, and you'll see that we're using like a 15 terabyte drive. But let's say it's a use case where 76 gigabytes per second isn't fast enough. Maybe they want to jump that up to 150. Then we just adjust the device count by one way that we can do that is just drop the device size down to a 7.68 terabyte SSD, and you can see that the performance doubled. And that's because Ceph is very good at linearly scaling performance. All the OSDs are a separate service, so we can just adjust these variables to go and hit all kinds of different performance requirements. If the performance isn't a concern and it's more a concern about saving money because you want to reduce the number of servers, then we'll go up to a bigger device size, and you can see we can cover that same amount of capacity, 1 petabyte, with just 4 servers by using the bigger drives. And you can see that brought the performance down, but still, this is still a great cluster. One other thing I wanted to touch on here is the importance of using Replica 3 for the IOPS that it brings. I'm going to show you really quickly adjusting this cluster to using erasure coding, and you're going to see the performance for write IOPS and read IOPS is going to crater. So here we go. This is right now at about 500,000 IOPS for the write IOPS, and we're going to change it to an erasure coding 2+2. And you can see our 500,000 went down to 100,000. So it's about a 60 to 80% drop in performance when you use EC. But I'm really looking forward to Tentacle because I think that's going to help bring that back up, and it won't be quite as bad. But today, anytime you're doing a workload that's IOPS focused, which again, virtual machines, containers, databases, you really want to use replica based because this is going to happen, and this is a great way to get an estimate on that. So let me jump to one more cluster design. Let me go back to the slides, and I'll show you the second one, this hybrid design. And this is great for, again, erasure coding is great for all kinds of, it was the everything else category of everything that's not compute. And let's take just a minute for it to come back up here. Any questions?
Yeah, Steve, while you're waiting on that, have you guys taken a look at any kind of a more concentrated erasure coding policy, like an 8+6 on only 4 nodes where you don't have a performance requirement? There's still some durability for a starter environment. I'm just wondering, I didn't see it in the model, so I'm wondering if you guys have even thought about it.
Yeah, we have been thinking about that recently. That's a really good question, John. One of the things that you can do is if you've got 4 nodes, today we typically will use a 2+2 erasure coding, but you can actually, if you go and increase the number of coding blocks, you can get more efficient than that. You can go and essentially do it instead of 1 pass over the 4 servers, you can do 2 passes, so you can have an 8 stripe length of erasure coding.
8+6 actually, so 8
Yeah.
K8 M6.
Yeah, well, I haven't thought about that specific one, but as you increase the erasure coding stripe length, you can essentially get more efficiency out of the same number of servers. And so if you lose a server, you lose 2 pieces. So that means that you have to have at least an M of 3 in this example of 4 nodes. You could have a stripe of, what would that be? It would be 5+3. Now you get more usable capacity, and you still have the ability to have a server offline with no downtime. And we haven't, but your example of like,
And I'm not suggesting
yeah,
it's a great idea. We're simply trying to respond to some entry-level requests that, hey, we want to get started. We only have a petabyte. It's lazy data.
yeah.
We shoehorn that into 4 nodes.
You can shoehorn it into 4 nodes, and you can do, I would generally just do a 2+2 and just keep it simple.
Yeah.
But when it's object storage that they're deploying, one of the cool things about that is you can move data from one storage class to another. So as the cluster gets bigger, maybe you start with 2+2 and they add a couple more nodes later, and now they're at 4+2. you can, behind the scenes, move all of that data around transparently and the customer doesn't even know. So object storage is one of the most flexible ways that you can deploy Ceph and move data around. With CephFS, it's a little trickier, but with object storage at least. And in fact, my second talk, we're going to actually set up, I'm going to show you a cluster where the data was put into the wrong place. It was put into Flash, and we're going to run a command that's going to move it all out of the Flash tier and into the erasure-coded tier. So we'll go from replica 3 to the other.
Appreciate it.
Yeah, great question. So this is a smaller cluster. It's just 4 nodes, and in fact, it's the 2+2 example. And this is a great way to solve, everything up to around a petabyte, and a half. This is a newer unit from Supermicro. It's got 6 NVMe bays in it, and the rest there's 30 hard drive bays. So it's a really nice combination of flash and platter. So it's one of our go-to units when it comes to Supermicro. And here you can see it's not flash, so it's getting 4.1 gigabytes per second. And again, if we want more performance, we can reduce the drive size, increase the device count. And here we're only using 14 of the 30 hard drive slots. And so we have room to go and add up to 15 more drives. So I'm using a 20 terabyte drive in this example. And again, the customer or use case was, hey, I need at least 8 gigabytes per second. One way that we can solve that is just double the device count. And you can see we just doubled the performance by doubling the number of spindles. I guess while we're in here, I should talk a little bit more about a couple of these levers before we wrap up. This here is the metadata data ratio, and what that's saying is that we want to have 2% of the cluster as flash storage so that we can have mirrored write log and mirrored MDS to offload those hard drives. Hard drives aren't going to do all the OSDs have an internal database that's called the metadata database, or the MDB, and we want to offload all of that into Flash. We also want to take the write log, which would normally be on the hard drive, and get that onto Flash so our writes complete faster. And then last but not least, we need some SSDs that are going to be there for the metadata pool, which is called the bucket index pool when you're doing object storage, or just the metadata pool when you're doing file. So that's what these sliders are for. And if you get it wrong, the tool will tell you. You're going to see a bunch of red text at the bottom. So if I go and move this down to 0 and I scroll down here, this is this device specification. This is where you're going to see all the warnings if you got the cluster design wrong. It's in here, it's telling us we don't have enough flash for this cluster to have it properly optimized. So I can just go and increase this a little bit, check again, and you can see the red text is gone, so the cluster is good to go. And yeah, by reducing the device, the device count, we got more performance, we got the right amount of flash. These sliders here for the RAM ratio, this is basically doing all the math behind the scenes to figure out, hey, how much RAM do I need to have for having 30 hard drives, or in this case, 28 hard drives per node. Sometimes you might want to adjust that up a little higher if you've got millions and millions of objects in a Ceph file system, hundreds of millions of files. You're going to need more RAM in those servers if they're going to run the MDS service on there. So the sliders are there to kind of adjust it for special cases, but just a bog standard deployment, you're going to be good to go with just what the tool recommends. These last sliders here are where you get to adjust the erasure coding. If you change this erasure coding from 2+2, 2+2, we're going to require 4 servers. If you change it to 4+2, we're going to require 6 servers. So we want to be able to stripe across at least that many servers. And so you might see a scenario where, like, why is it putting so many servers in there with the drives not being properly, all the slots aren't being filled? And that's because this also designates the minimum number of servers for that erasure coding. So 6+2 is 8. So you can see it allocated 8 servers, even though it's only putting 10 hard drives in per. So keep those things in mind as you adjust things. And then the backfill, I want to talk briefly about that. Your backfill should always be 10%. And that's because Ceph repairs itself by using free space. And so if you don't have free space for the cluster to kind of move things around as drives fail and it needs to rebalance, then you get into an out of space condition effectively. The OSDs try to keep within a couple of percent of each other when you've got the cluster properly balanced, but when you have a device failure, it's going to get a little bit out of balance, and you always want to have like that 10% margin. And so when you have this design, the design tool set to 10%, and you say, I want 500 terabytes, you'll notice over here that it goes and it actually makes a usable capacity cluster of 620. And that's because it's adding 50 and then rounding for the different drive sizes and all of that. So it makes sure that you are designing for what the customer or end user really needs, and not forgetting about the amount of free space that's needed for that auto repair. And then the last one, this is a fun one. I'll bring up the Core Vault one. And you know, as Dan was getting at, there's exabyte size environments out there. And one of the challenges with Ceph is that, you know, if you choose 8+3 or 8+4, that means with like, say 8+4, that means that you could lose 4 hard drives across different nodes, and or you could lose 3 across different nodes of a cluster. If you lost 4, the cluster's going to stop. And 4 hard drives in an 8+4 layout, that's pretty easy to hit if there's 4,000 drives in the cluster. And so you end up having to add more and more coding blocks, and it makes the cluster more and more inefficient. And so there's a technique that you can use to work around that, and that is to use localized erasure coding in the hardware before you put the distributed erasure coding on top with Ceph. So let me bring that up real quick here, and I'll show you guys what that cluster architecture looks like. And it doesn't have to be a Core Vault. You can use other localized RAID techniques, and there's even some erasure coding techniques. Gerasure is the default within Ceph, but there's also some layouts, some erasure coding layout options within Ceph that'll let you do localized erasure coding to do the repairs locally, purely using all Ceph. We really like this independence, though, where we can use some of this tech inside the hardware. This particular unit we really like because it can get back to full health in 5 hours. So you don't have to sit there and worry about, okay, how long is this cluster going to be back to full health? Well, from the cluster's perspective, it's at full health all the time because the individual drive failures don't percolate up into the virtual devices that come out of the Core Vault. So this Core Vault, it's got 106 hard drives in there. Internally, it virtualizes that down to whatever we want. Typically, we'll reduce that down to 40 drives. And those are all fault-tolerant drives. So a drive fails, those 40 are still solid. Internally, the box just goes and heals itself, and 5 hours later, we're all back to 100% health within the box. So the cool thing there is like, you can lose 2 drives per internal pool in these boxes, and sometimes we typically set it up with two separate independent pools per box. That means you can lose 4 drives on this with 0 downtime across 36 nodes, which means I can lose 36 times 4, which is like 144 hard drives at the same moment, and the cluster didn't even skip a beat, and it's still running. So this kind of durability takes you from 6 nines to 14 nines. And this is what you need to do when you're starting to talk about managing clusters at that scale of tens of petabytes to hundreds of petabytes, because it really transforms the whole equation and makes it operational at scale, where you can actually sleep and take vacation and not have to worry about bringing in experts to do a lot of fancy maintenance on the cluster. So yeah, this you'll see that on this, this is a specialized design utility we put together for Seagate, and you'll see down below there's special erasure coding options here that take into account like 8+2 over the top of Core Vault 16+2. And you'll see it, depending on which layout we choose, it's more or less efficient. And so in this case, it's 38 servers to get to 50 petabytes. But anyways, that's kind of a look at how to really take Ceph to a much larger scale with super high durability. And the design utility, you can just kind of move the sliders around to get whatever capacity need You need, and I guess the very last thing is we added a power estimator in there as well this last year, so you can go in and click on that and put in your power in terms of watts per, cost per terawatt or kilowatt hour for your data center and get a rough idea there. Yeah.
This technology sounds amazing. What's the delta on like the intelligent box versus?
That is one of the coolest things. Seagate makes it the same price as their JBOD.
No.
Yes, it's a zero uplift. So it's kind of very, very cool in that way. And we discount our licensing for the QuantaStore product as well, so it makes it a wash. Because we really want everybody having that level of durability. It makes our life easier, the customer's life easier. It's just this is a really nice win-win-win. So, yeah, it's not I think not very well known out there, but it is a fantastic way to scale. All right, thanks everybody. Yeah.